Okay. So, let's start now with a different topic. Let's say an evolution of the topics that we covered so far, which is coupled dark energy. So, as we've seen also in the recap, we are assuming a self-interacting scalar field with no other interaction. So, in the Lagrangian, there was just a self-interaction term and the potential characterizing our fluid, our quintessence model. Now what we're going to do is to introduce an interaction term with matter. So there's going to be matter interacting with dark energy. Coupled dark energy. Okay, so first of all, why? Why should we do something like that? Well, we see that nowadays omega m and the density of matter and the cosmological constant are quite similar. So, combinato, okay, we have all the tracker solutions and all that and so on, but why not? They could be actually coupled. That's why they are physically following one each other, they're influencing one each other. And therefore, it might be relevant to introduce coupled dark energy. Okay, because it could be that. We started with the simplest thing, but maybe nature is a little bit more complicated than that. And therefore, a coupling term might be present. So what we do, if we want to introduce a coupling term, well, we just have to change the action of our fluid. Therefore, we have the action that contains the universe, that it contains the Lagrangian of, so we have our four-dimensional volume, and then we are going to have the Lagrangian of of gravity, for course. I mean, we have the Ricci scalar that contains the gravity term, and then we can have the Lagrangian for our potential and the Lagrangian for a matter component. You can split it in radiation matter, whatever you want, but basically we have a matter component. That's what we are going to consider at the moment. One matter component and the cosmological constant. So what we have to do? Well, we need to introduce interaction term into these two terms. Once you have your interaction term, you can plug your Lagrangian, newly defined, into to derive the corresponding energy momentum tensor. What's happening? If we have energy conservation, what we have? We have the nu equal to 0. Okay? A certain fluid, let's say phi, is conserved. And the same goes for matter, the nu matter equal to 0. But now if they're interacting, what happens? Are these two quantities conserved? No. Why? Because they can exchange energy momentum. If there is no interaction, they cannot change energy momentum. They are not touching really one each other. But if there is an interaction term, they can exchange momentum. I don't know. I hit this bottle, I'm transferring my energy to the bottle and the way around. Okay? Therefore, if we introduce an easy way to introduce a coupling between two different species is to introduce a current between the two. Okay, it's just a current that provides the transfer of the energy. But now we have a global energy conservation, right? Therefore, we have the nu for total, so all of it has to be conserved. So what do you think should be this guy here? Minus J mu. You see? We have an energy momentum exchange between these two guys. Now, an example that I'm going to show you how it pops up from scalar tensor theories. So this is kind of a natural result of scalar tensor theory. Is a current due to this coupled J, which has a proportionality constant that we are going to assume to be universal. Okay? Universal means that there is no dependency nor on the position nor on time. Okay? It's just a number, universal. And then we have the trace of the matter component and the represent the potential of the scalar field. That's one way to introduce the coupling, very simple form, and this is an example. There are also nonlinear couplings and crazy stuff out there. Okay? Now we keep this one because it's simple. We can have some analytical expression that we can treat and understand the meaning of what's going to happen. And that is also motivated by scalar tensor theories. Okay, so there is a motivation of introducing such a tensor. Okay. Then, what do we see out of this expression? Well, we have some constraint that we can impose to it, because here we have a gradient, right? And therefore there is going to be a direction, a preferred direction, somewhere in the universe, okay? And what we want to do now is to keep the E terms equal to 0. Nu equal to 1, 2, and 3, we expect our G E, then E, otherwise, we would have an energy momentum flux directed somewhere, and this would break isotropy. Okay. Then here there is a complication that I'm going to treat later on, which is related to baryons. Because if we have a coupling for baryons which is non-zero, then we might have the mass of electrons that is evolving as a function of time, as we're going to see. And if this is the case, then we need to reinterpret all our spectroscopy, because the position of the lines in the transition between the electron levels in an atom depends on the mass of the electrons. And if the mass of the electron is evolving as a function of time, these lines are going to shift. Now what's the problem? How do we interpret cosmological redshift? If I see a line which is shifted, it's not anymore due to the expansion of the universe, but is due to this interaction term that is going to give you an evolution in the mass of the electrons. Okay? Therefore, for simplicity, now we are going to, when I speak about matter, I mean one individual fluid, and I'm not thinking of baryons. Later on, we are going to split these two components, and I'm going to show you better where are these complications arising. Now I'm just telling you the simpler picture that we are going to take. But matter could be also radiation. But look at this construction. Due to the structure of the energy momentum tensor of the electromagnetic field, what is the trace? 0. For our radiation field, J, for radiation, is equal to 0. This is just because of the structure of the electromagnetic field itself. Yes?
So wondering, you said Ji to be 0 to preserve isotropy?
Yes.
But we have a minus for the phi, so doesn't they cancel out? So if we have Ji for matter and minus Ji for the phi, they cancel out and we start.
Well, I mean, here we just have this expression where here we have when nu is equal to 0, this is just 0. For the time components, then this is different than 0. The minus remains on the zeroth equation. Okay. Good. But now let's think about it. What's the consequence if we have this interaction? Okay, we have something. Yeah.
Question, please. Because of the baryon coupling problem, we are assuming that the energy is coupled only with that matter, or
There are ways to deal with that. Okay. There are two ways. One is let's take it easy. Q is equal to 0 for baryons for some reason. Okay, so we're just hiding the problem, or let's say there's not a problem there. Or we say that we can introduce coupled dark energy, which has some screening mechanism that I'm going to introduce later on, which are related to the behavior of Q as a function of position. Okay, because whenever we are measuring a spectra, or in our laboratories and so on, we are in a specific place in our universe that are extremely overdense. Okay, the emission given within a galaxy, there is the gravitational potential of a galaxy. Here, there is the gravitational potential of Earth. And the interaction, and one can introduce the interaction such that when we are in overdense region, there is an effective coupling Q, which is 0 or negligible. So you are far away, you have Q is active. If you are approaching an overdense region, it's not active anymore. That's called screening. Okay? That's one way. So you can keep an interaction term, but where there start to be problems with baryons, there is not interaction because of the screening mechanism. Okay? We are going to see the screening mechanism. The other thing that one could do, this is what I wanted to show you later. But anyway, what one could do instead was to move from the Einstein frame to a Jordan frame, in which the coupling of the baryons is not there anymore. Okay, there is a way of reshuffling using conformal transformations that helps you to keep the coupling constant for baryons equal to 0 and the other ones different than 0. But I'm going to show you that. Okay, so there are, let's say, 3 ways to address this problem. So baryons are a problem, or an issue, not a problem. And you can do it by treating the coupling of the baryon equal to 0, identically 0, by construction. You can have a chameleon mechanism in which the coupling, in general the coupling, could be matter, baryons, and so on, whatever, is density dependent. And if it is density dependent, it means that it is spatial dependent. And this can go to 0 if ρ is large. That's a screening mechanism. Or you can say, okay, QB is different than QA. I do not have a screening. And to save all the interpretation of the observation coming from spectroscopy, for example, then I can use this conformal transformation to rephrase the equation such that the baryonic component is conserved and the other ones are not. There is a mathematical way to do that. Okay? I'm going to show you this later.
coupling dependent on position wouldn't violate SO.
Sorry?
Coupling that depends on position wouldn't violate SO.
Phi would be, we're going to see that. I mean, we're going to, I'm anticipating a little bit too much. Just keep in mind, what I want to show you here is that we are introducing a coupling term, which is simple and it's motivated by scalar tensor theories. We have to take care of baryons, and in details we are going to do it later on. Okay? For the moment, keep in mind that we just have a scalar field and a matter component. And with matter component, now you can think at matter, because there is no coupling with radiation. Where is it? Where did I put it? I didn't. The radiation, so we can call it matter, and with radiation, that's equal to 0. Okay? That's because the trace of the electromagnetic field is equal to 0. Good, let's move on. clear. We are going to use our field. We are going to use the matter component, and we can also keep radiation. It doesn't matter. It doesn't participate to the coupling. This we can do. Je are equal to 0, again for isotropy. And I'm going to set the constant that enters in GR, you know, it is 8 pi g divided c to the power of 4, that we call k to the power of 2, and that's going to be equal to 8 pi g over c to the power of 4. I'm going to impose it, I'm going to use c and c such that this is equal to 1. Okay, so that I don't have this annoying term to drive around. Good. Now that we have our expression with our coupling, we can look for the equation of motion and see how these fluids are going to behave. And to do that, the simplest thing we can do is to use the continuity equation. Continuity equation that is given by the mu equal to 0 term. Right? That's the density, how the density is behaving, how the energy is behaving. Mu, T, mu, 0 for our field. Where do I put it? Properties indices. I'm going to put the label Q, T, M. No. And then we have the same for T mu 0 for metal is equal to plus Q T M del phi. Radiation is going to be equal to 0. Let's put it here. Radiation mu T mu 0 for radiation is going to be equal to 0, and then that's it. Okay? So you see this is one equation. We can now express it in terms of the density. We plug here the energy momentum tensor as is specified, and as we already did it, I think 3 times by now, they are rho phi plus 3h rho phi plus p phi equal to minus q rho m phi dot. For metal, we have rho dot plus 3h rho r plus p. Now that's metal, so 0. So that's pressureless. Metal and metal. Okay, pressureless. Therefore, this is just rho metal equal to the plus q rho metal p dot. Okay, for radiation, we have our usual conservation. So rho dot radiation plus 3h rho radiation plus pressure of radiation equal to 0. What do you see? Look at the continuity equation. We have a source term. We have a source term. And we're going to see later how this is related to a force, to an effective force. Okay, the fifth force. There is an interaction. Therefore, our metal is not anymore free. If you take a free-falling object, why is free? It's free-falling in the gravitational field. But now there is an interaction with the dark energy field. Therefore, it feels an external force. It feels a fifth force. And therefore, a free-falling object is not anymore free. There is this external force, and if you take a dark energy, photons will follow the geodesics, but matter is not going to follow geodesics. You drop them, there is the interaction with gravitational, with the dark energy, and this is going to be, gives you a deviation from the geodesics. Okay? Then we have our continuity equation that we can express in terms of the potential, right? Because we have a rho phi, which is equal to 1/2 phi dot square plus v, and then pressure of phi is equal to 1/2 phi dot square minus v, right? So we just have our rho and p, and we plug it where it's appearing. Right? That's something that we already did. If we do that, we arrive at the continuity equation expressed in terms of the scalar field. Where up to 9, now our Klein-Gordon equation adds 0 here. Now we understand that there is this term popping up. Minus q rho. Okay? The phi dot disappears because it appears on this, and this term when we do the derivatives. Okay? Therefore, this is your Klein-Gordon equation for your coupled vacuum energy. Klein-Gordon. Then what we do? The usual stuff, right? All what we did so far with the dark energy, we are going to do it again. So we are going to study, now just the time is up, so I'm just going to anticipate what we are going to do. We are going to study the phase space, which is going to become a little bit more complex, unfortunately, okay? Because the coupling have to be, we need to deal with the coupling as well. And because now we are going to include radiation, you see? So we need to use also the radiation term. Therefore, we are going to use our phase space, where we have x1 and x2, that are usually related to the kinetic term of dark energy, the potential of dark energy. But we are going to have also an x3, which is related to radiation, dark energy, and this is radiation. Okay? And we are going to see, I'm going to show you all the critical points that are 7, I think, or even 8, now I don't remember. So there are a pile of critical points that we are going to study and see which one are valuable. There are some that are physically valuable, they will make sense, but they are excluded by observations. For example, the baryonic nucleosynthesis or local gravity constraints are imposing limits on the value of Q that are allowed, and therefore those critical points are not there. Okay? For some reason the universe is not falling there, it's not going across those points. And we are going to see those that are going to give you a natural evolution between radiation domination, matter domination, and eventually a field-dominated epoch. Okay? Yeah, that's it. And then, as last, I mean, already mentioned it earlier, but let's conclude the picture. We are going to discuss the case of baryons. Okay? Baryons are an issue. Because, and you see it immediately from this expression, because when we were dealing with, we solve with a rho, right, as a function of the time evolution, so we would have with Q equal to 0, we would get that the density goes as a to the power of minus 3. Right? That's equal to 0. That's what we know. But if this term is different than 0, then this is not the case. The density is evolving in a different way. But we are going to see that if Q is different than 0, then our density is evolving as a to the power of minus 3, and then we have a function of a, which is due to the interaction. Okay? Therefore, what one could do is to interpret, that's rho equal to rho 0, so let's introduce also this one so we have the full expression. One can think of the fact that the mass of the particle is evolving as a function of time. Okay? Which give us all the problems that we mentioned. Okay? But this is going to be done later. So that's the part that we're going to do. We introduced coupled dark energy by plugging in an interaction term, an exchange of energy momentum between matter and the field, of dark energy field, which, as an example, we took like that. So that's the energy density flux exchange, the exchange between the two guys, and this is motivated by scalar tensor theories. Okay? So there is a motivation there. Then by imposing isotropy, we know that the JE term must be equal to 0, otherwise we would have an energy density flux pointing somewhere. And once we have this construction, we can look at the only equation which is left describing the dynamics, right? Which is the zeroth equation. Well, there's also the other one, but the relevant is the continuity equation, which is the zeroth equation of these three guys here that give us this expression with a coupling term between the two that is popping up. So that's the only difference between the previous results we had and what is coming out with the coupling. And radiation is untouched because the because the energy momentum tensor of radiation is traceless. Okay, so we have a 0 here. And with that, once we have our Klein-Gordon equation expressed in terms of the field, just by using the definition of rho and P for dark energy, we can study our phase space, including radiation, and see how the universe is going to evolve between radiation, matter, and field domination epoch, including the baryons. And as last, I'm going to treat the baryons and see what is the real complication, which is coming from this equation here, from this term here, because the density is not anymore evolving as a to the power of minus 3, but is actually an additional term. And this term, if you put it together with rho 0, can be interpreted as an evolving mass for the particles. And this screw up our observations until, unless we introduce a scaling mechanism such that Q for baryons is negligible, well, it matters, or we can live with that and play with conformal transformations to keep the energy momentum density, the energy momentum tensor conserved for baryons, but not for the other species. Okay, so there are mathematical tricks to do that. Okay, good. So we can stop here. Thank you very much, and I'll see you next week. Ciao, arrivederci.
I have a question on the previous lecture. How did you get this eigenvalues? So how did you get these eigenvalues here?
So if you go up a little bit. So here. here. So you have, so basically you have the full equations that can be solved only numerically. So what we did was to use a perturbative approach and put ourselves in the vicinity of the critical points. So it is at things at the critical points.
Yeah.
And then we are asking ourselves what happens when we are in an immediate vicinity of them. So that's a perturbative approach. We just plug in these x1 and x2 in this way into these expressions. So you see, where is it? Yes, in this expression, x1, x2, x1, x2. And we keep only first order terms.
Okay.
Okay? And we basically split a term that is referring to the critical points, but they are equal to 0 by construction because they give you a time derivative which is equal to 0. And then we have the perturbation, which is the one that we care about. And they are only the one at first order.
Yeah.
First order in the x1 and the x2. Okay? And this gives you a linear differential equation of this sort. So we are linearizing the problem. Okay? And then we just compute the eigenvalues and eigenvectors of this equation. Because if we now solve this very simple differential equation, that's the solution that we get.
Okay.
And therefore, the eigenvalues tells you how the evolution, how the solution is, what are the properties of the solution.
Okay, yeah. Yeah, I got it. So we will linearize it, and then from that equation we will write of the matrix A, and then...
Exactly, because the eigenvalues are popping up in the solution, in the general solution.
Also, I have one more question on the...
So let me finish the recording.